welcome to this problem walkthrough. Today, we will be tackling problem number 1066, Campus Bikes 2. This is a fascinating problem that challenges us to think critically about optimizing assignments. Let's explore the problem, analyze different approaches, and solve it step by step. Ready? Let's dive in. In this problem, we are tasked with assigning bikes to workers in a way that minimizes the total Manhattan distance. The scenario involves n workers and m bikes, each represented as a point on a 2D grid. The Manhattan distance between 2 points, say, x1, y1, and x2, y2, is calculated as the absolute difference of their x coordinates plus the absolute difference of their y coordinates. The goal is to ensure that each worker gets exactly one bike, and no bike is assigned to more than one worker. The result we need to return is the minimum possible sum of these distances. To process this input, we are given two lists, workers and bikes, where each element in these lists represents the respective positions as 2D coordinates. The output is a single integer value representing the minimized sum of Manhattan distances after the optimal assignment of bikes to workers. Let's look at an example to understand this better. Suppose we have 2 workers and 2 bikes. The workers are positioned at 0, 0, and 2, 1, while the bikes are located at 1, 2, and 3, 3. Here, worker 0, at position 0, 0, is assigned to bike 0, which is at 1, 2. The Manhattan distance for this assignment is calculated as 0, 1 plus 0, 2, which equals 3. For worker 1 at 2, 1, the assigned bike is bike 1 at 3, 3, with a distance of 2, 3 plus 1, 3, also equal to 3. Adding these distances gives a total of 6, which is the output for this example. This demonstrates how the assignments are made to minimize the sum of distances. Here's another example. This time, we have 3 workers at positions 0, 0, 1, 1, and 2, 0, and 3 bikes at 1, 0, 2, 2, and 2, 1. Worker 0, at 0, 0, is assigned to bike 0 at 1, 0, resulting in a Manhattan distance of 0, 1 plus 0, 0 equals 1. Worker 1, at 1, 1, is paired with bike 2 at 2, 1, producing a distance of 1, 2 plus 1, 1 equals 1. Finally, worker 2, at 2, 0, is matched with bike 1 at 2, 2, with a distance of 2, 2 plus 0, 2 equals 2. Adding these distances gives a total of 4, which is the output for this case. This example highlights the importance of strategic assignments to achieve the minimum total distance. Now consider a simpler example with just 1 worker and 2 bikes. The worker is located at 0, 0, while the bikes are at positions 2, 1, and 1, 2. To minimize the distance, the worker is assigned to bike 1, which is at 1, 2. The Manhattan distance for this assignment is calculated as 0, 1 plus 0, 2, which equals 3. Since there's only 1 worker, the total distance is simply 3, which is the output. This case demonstrates how the algorithm handles situations where there are more bikes than workers. We also have some constraints and edge cases to consider. The number of workers and bikes is between 1 and 10, and each position is represented as a pair of integers within the range of 0 to 999. Edge cases include scenarios like having only 1 worker and 1 bike, where the solution is straightforward. Another edge case is when all workers share the same position, requiring careful assignment of bikes to minimize distances. Similarly, when all bikes are at the same position, the assignment must be optimized for worker positions. Finally, when workers and bikes are positioned far apart, the algorithm must calculate large distances accurately. These considerations ensure the solution works under all possible input conditions. Here we begin by examining different approaches to solving this problem. The brute force approach might seem intuitive at first. It involves trying every possible way to assign the workers to the bikes. Since there are n workers and m bikes, we can generate all possible permutations of these assignments. For each assignment, we compute the total Manhattan distance, and then we track the minimum distance across all permutations. While this guarantees correctness, the factorial complexity, O(m), for m bikes makes this approach computationally impractical when the number of bikes is large. The key takeaway here is that the problem is fundamentally about finding the optimal assignment of workers to bikes, but attempting to explore all permutations quickly becomes infeasible. To improve upon this, we can consider backtracking with pruning. This method incrementally builds assignments by assigning one worker at a time, calculating the partial cost at each step. If the partial cost exceeds the current minimum, we stop exploring that branch altogether. By pruning these unpromising paths, we reduce the number of combinations to explore. However, even with pruning, this approach can still become computationally expensive in the worst-case scenario. To address these limitations, we turn to a more efficient solution: dynamic programming with bit masking. This approach uses a bit mask to represent which bikes are already assigned, allowing us to systematically track and evaluate different combinations. For any given state, defined by a pair, worker_index, bike_mask, we store the minimum cost of assigning the first worker_index workers to the bikes indicated by bike_mask. The transition formula helps us compute the cost for new assignments. For each worker I in each bike j that isn't yet assigned, we calculate the minimum cost for the current state by considering the cost from the previous state plus the Manhattan distance between the worker and the bike. The base case of this process is straightforward: when no workers are assigned, the cost is 0. In terms of complexity, this approach is much more efficient compared to brute force or backtracking. The time complexity is n*2 to the power of m, and the space complexity matches this at n*2 to the power of m, which is manageable given that the number of bikes m is typically small. This makes DP with bit masking particularly appealing because it avoids redundant calculations using memoization, thereby balancing clarity and performance. Now let's compare these approaches and understand the trade-offs. Brute force, while simple to implement, is computationally overwhelming due to its factorial complexity. On the other hand, backtracking with pruning can be more memory efficient, but it still struggles with exponential growth in the number of combinations, especially for larger inputs. Dynamic programming with bit masking stands out because it strikes the perfect balance for this problem. It is ideal for scenarios with a small number of bikes m but a potentially larger number of workers n. By leveraging the pre-computed structure of the DP table, it avoids the inefficiencies of brute force and the lack of structure in backtracking. Overall, DP with bit masking is the most practical solution for this problem, providing clarity, efficiency, and scalability, making it well suited for the constraints and requirements of campus bikes too. In this problem, we are tasked with assigning bikes to workers on a 2D grid in a way that minimizes the total Manhattan distance. The Manhattan distance for a worker-bike pair is calculated as the sum of the absolute differences between their x and y coordinates. The condition is that each worker can have only one bike, and each bike can be assigned to only one worker. To solve this, the brute force approach involves exploring all possible assignments. First, we understand the problem by recognizing that the total cost is the sum of Manhattan distances for all assigned pairs. The goal is to find the assignment with the smallest total cost. To achieve this, we generate permutations of bike assignments based on the number of workers and bikes. For example, if there are fewer workers than bikes, we generate all combinations of assigning a subset of bikes to the workers. Then, for each permutation, we calculate the total distance by summing up the Manhattan distances for each worker-bike pair. This systematic exploration ensures that we evaluate all possible configurations, even though it may be computationally expensive for larger inputs. Once we have the total distance for a specific assignment, we compare it to a variable initialized to infinity, called min_distance. If the current permutation's distance is smaller, we update min_distance. This allows us to keep track of the best assignment we've encountered so far. After iterating through all permutations, the value of min_distance will represent the minimum possible total distance, which we then return as the result. Brute force is an exhaustive approach and guarantees the optimal solution since it evaluates every possible pairing. However, it's computationally expensive due to the factorial growth of permutations. For instance, if there's only one worker or one bike, the solution is trivial, as we simply calculate the distance between the given pair. The brute force approach is a good starting point for understanding the solution but is impractical for larger inputs. This is where optimizations like greedy methods or dynamic programming come into play, enabling us to handle larger instances more efficiently while potentially sacrificing the guarantee of an optimal solution. To implement this algorithm, we use a few key data structures. The worker and bike coordinates are stored as tuples in a list, which allows us to quickly compute Manhattan distances. A permutation generator, such as Python's itertools.permutations, is used to create all potential assignments of bikes to workers. For n workers and m bikes, the generator produces m/mn permutations when n is less than or equal to m. Additionally, we use simple variables like min_distance to keep track of the smallest distance observed so far and current_distance to compute the cost of a single permutation. The key operations in this algorithm include computing the Manhattan distance for each worker-bike pair, which is done in constant time for a single pair, and generating permutations, which is the main computational bottleneck. Summing up the distances for a single assignment involves iterating through the workers, making the operation linear in the number of workers, though this summation is repeated for each permutation, contributing to the overall complexity. The complexity of the brute force approach highlights its limitations. Generating all permutations requires O(m) time, where m is the number of bikes. For each permutation, we calculate the total distance, which involves iterating through n workers. This results in an overall time complexity of O(n*m). The space complexity is dominated by the storage of permutations, which is also O(m), while other auxiliary variables like min_distance require only constant space. These characteristics make brute force infeasible for large values of n or m, as the factorial growth quickly becomes unmanageable. Additionally, storing all permutations can be memory intensive. To better understand the mechanics of this algorithm, let's look at an example. Suppose we have two workers at coordinates 0, 0, and 2, 1, and two bikes at coordinates 1, 2, and 3, 3. We'll walk through how we generate permutations, calculate distances, and determine the optimal assignment. For the given input, the first step is to generate all permutations of bike assignments for the two workers. The possible assignments are worker 1 takes bike 1 and worker 2 takes bike 2, or worker 1 takes bike 2 and worker 2 takes bike 1. Next, we calculate the total distance for each assignment. In the first assignment, worker 1 is assigned bike 1, and worker 2 is assigned bike 2. The distances are calculated as 0-1 plus 0-2 for the first pair, and 2-3 plus 1-3 for the second pair, resulting in a total of 6. In the second assignment, worker 1 is assigned bike 2, and worker 2 is assigned bike 1. The distances are 0-3 plus 0-3 for the first pair, and 2-1 plus 1-2 for the second pair, resulting in a total of 8. Comparing these, we find the minimum distance is 6. This example illustrates how brute force guarantees correctness by evaluating all possibilities, but it also demonstrates the computational expense, especially as the number of workers and bikes increases. This Python implementation solves the Campus Bikes 2 problem using a depth-first search (DFS) approach with memoization to optimize the solution. First, we calculate the Manhattan distance between any worker and bike, which is the sum of the absolute differences of their coordinates. The Manhattan distance is used to assess the cost of assigning a bike to a worker. The DFS function is used to explore all possible assignments of bikes to workers. It takes two parameters, worker_index, which tracks the current worker being considered, and bike_mask, a bit mask that keeps track of which bikes have already been assigned. 1. Base case, if all workers have been assigned bikes, worker_index == n, the function returns 0 because there's no further cost to add. 2. Recursive exploration, for each bike that hasn't been assigned yet, checked via bike_mask, the algorithm calculates the Manhattan distance for assigning the bike to the current worker. It then recursively calls DFS for the next worker, updating the bike_mask to indicate that the current bike is now taken. 3. Memoization, to avoid recomputing results for the same worker and bike assignments, the @row_cache decorator is used. This significantly reduces redundant calculations and improves runtime performance. For minimization, the function tracks the minimum total distance across all valid assignments using the min_distance variable. Finally, the DFS function is called starting from the first worker, worker_index =0, with no bikes assigned, bike_mask =0. The result is the minimum sum of Manhattan distances for assigning all workers to bikes under the given constraints. This algorithm effectively explores all possible assignments but leverages memoization to handle overlapping subproblems, achieving an optimized solution. The time complexity is reduced to approximately n*2 to the power of m, where n is the number of workers and m is the number of bikes, making it feasible for the problem's constraints. Here, we begin by defining our Java solution to the problem. The AssignBikes method takes in two 2D arrays, workers and bikes, representing the positions of workers and bikes respectively. First, we calculate the number of workers, n, and the number of bikes, m. Then, we initialize a memoization map, memo, which will help us store and reuse results for overlapping subproblems. The core of the solution lies in a recursive helper method called DFS. This method is tasked with finding the minimum total distance for assigning bikes to workers. We begin the recursive process by calling DFS with the first worker, an initial bike mask of 0, which indicates that no bikes have been assigned yet, and passing along the workers, bikes, and memo map. Within the DFS method, we check if all workers have been assigned bikes by comparing worker index to n. If so, we return 0, as no more distance needs to be calculated. To optimize the recursion, we use a key composed of the current worker index and bike mask, and if the result for this key already exists in memo, we simply return it. Next, we initialize min distance to the maximum possible value. We then iterate over all bikes, represented by index b. Using bitwise operations, we check if a bike has already been assigned by examining the bike mask. If not, we calculate the Manhattan distance between the current worker and the bike using the helper method Manhattan distance. This distance is added to the result of a recursive call to DFS, where we move to the next worker and update the bike mask to mark this bike as assigned. We update min distance with the minimum total distance found. Finally, we memoize the result for the current key and return min distance. The Manhattan distance method itself calculates the distance between a worker and a bike using the absolute differences in their x and y coordinates. To begin, we are solving for the minimum distance required to assign bikes to workers. In this example, we have two workers at positions 0, 0, and 2, 1, and two bikes at positions 1, 2, and 3, 3. The process starts by calling the depth-first search function, DFS, with worker_index set to 0 and bike_mask set to 0, indicating that no bikes have been assigned yet. For the first worker, we iterate over all available bikes. Assigning bike 0 to worker 0 involves calculating the Manhattan distance, which is the absolute difference of their x-coordinates plus the absolute difference of their y-coordinates, 0-1 plus 0-2 equals 3. The function then recursively calls DFS with worker_index increment to 1 and the bike_mask updated to 1, signifying that bike 0 is now assigned. Similarly, assigning bike 1 to worker 0 results in a Manhattan distance of 0-3 plus 0-3 equals 6, and the function makes another recursive call with worker_index as 1 and bike_mask updated to 2. Moving on to worker 1, for the case where bike 0 is already assigned, the only remaining option is bike 1, which has a Manhattan distance of 2-3 plus 1-3 equals 3. At this point, both bikes are assigned, reaching the base case, which returns 0. The total distance for this assignment becomes 3 plus 0 equals 3 for worker 1. For the alternate scenario where bike 1 is assigned to worker 0, the only option left for worker 1 is bike 0. Here, the Manhattan distance is computed as 2-1 plus 1-2 equals 2. With both bikes assigned, we reach the base case and return 0. The total distance for this assignment becomes 2 plus 0 equals 2. Comparing the distances for worker 1 across the two assignments, the minimum distance is 2. Backtracking to worker 0, we calculate the total distances for each bike assignment. If bike 0 is assigned to worker 0, the total distance is 3 plus 3 equals 6. If bike 1 is assigned, the total distance is 6 plus 2 equals 8. Among these, the minimum distance is 6. Therefore, the output for this example is a minimum total distance of 6. Now, let's look at another example where both workers are at the same position, 0, 0, and there are two bikes at 1, 0, and 2, 0. Starting with worker_index 0 and bike_mask 0, the function begins by iterating over the available bikes. Assigning bike 0 to worker 0 results in a Manhattan distance of 0-1 plus 0-0 equals 1. A recursive call is made with worker underscore index increment to 1 and bike underscore mask updated to 1. Similarly, assigning bike 1 to worker 0 gives a Manhattan distance of 0-2 plus 0-0 equals 2, and the function proceeds with another recursive call. For worker 1, when bike 0 is already assigned, the remaining option is bike 1, with a Manhattan distance of 0-2 plus 0-0 equals 2. Once both bikes are assigned, we reach the base case, which returns 0. Adding the distance for worker 1 to the previous calculation, the total distance becomes 2 plus 0 equals 2. In the other scenario, where bike 1 is assigned to worker 0, the only option for worker 1 is bike 0. The Manhattan distance for this is 0-1 plus 0-0 equals 1. With both bikes assigned, the base case is reached, returning 0. The total distance becomes 1 plus 0 equals 1. Backtracking to worker 0, we evaluate the total distances for each bike assignment. If bike 0 is assigned to worker 0, the total distance is 1 plus 2 equals 3. If bike 1 is assigned, the total distance is 2 plus 1 equals 3. Therefore, the minimum distance in this case is 3. The output for this example is a minimum total distance of 3. In the next example, we consider a single worker located at 0, 0, and 3 bikes located at 1, 1, 2, 2, and 3, 3. Starting with worker underscore index 0 and bike underscore mask 0, we iterate over the bikes. Assigning bike 0 to the worker gives a Manhattan distance of 0-1 plus 0-1 equals 2. A recursive call is made with worker underscore index increment to 1 and bike underscore mask updated to 1. Since there is only one worker, the base case is immediately reached, returning 0. The total distance for this assignment is 2 plus 0 equals 2. Next, assigning bike 1 to the worker results in a Manhattan distance of 0-2 plus 0-2 equals 4. Another recursive call is made, and the base case is reached, returning 0. The total distance for this assignment becomes 4 plus 0 equals 4. Finally, assigning bike 2 to the worker involves calculating the Manhattan distance. The Manhattan distance for assigning bike 2 to the worker is 0-3 plus 0-3 equals 6. And a recursive call to DFS is made with worker underscore index set to 1 and bike underscore mask updated to 4. Once again, the base case is reached, returning 0. The total distance for this assignment is 6 plus 0 equals 6. Among all the assignments, the smallest total distance is 2, which occurs when the worker is assigned to bike 0. Therefore, the minimum total distance for this example is 2, and this concludes the process for this case. The time complexity of our solution is driven by the depth-first search with memoization. To break it down, the number of unique states in the DFS depends on two parameters, the worker index, which can range from 0 to n1, and the bike mask, which tracks the assignment of bikes using a bit mask. Since there are n workers and 2 to the power of m possible states for the bike assignments, the total number of unique states is n multiplied by 2 to the power of m. For each of these states, the algorithm iterates through all m bikes to find unassigned ones and calculate their Manhattan distances, which takes m time. Therefore, the overall time complexity is determined by multiplying the number of states, n times 2 to the power of m, by the work done per state, which is m. This gives us a total time complexity of n times m times 2 to the power of m. The time complexity of n times m times 2 to the power of m represents the dominant factor in the runtime of this algorithm. While the memoization reduces redundant calculations, the exponential factor of 2 to the power of m makes the solution computationally expensive for larger inputs. Shifting our focus to space complexity, the solution requires space for the recursive call stack and the memoization table. First, the recursion depth is equal to the number of workers, n, because each recursive call process is one worker. This contributes n to the space complexity. Second, the memoization table stores results for all possible combinations of worker indices and bike masks. With n workers and 2 to the power of m bike masks, the table uses n asterisk 2 to the power of m space to store the states. These two components dominate the space usage of the solution. In addition to the recursion stack and memoization table, there is minimal space used for local variables and intermediate calculations inside the DFS function. However, this space is negligible and does not impact the overall complexity. Therefore, when we consider the total space complexity, it is dominated by the memoization table, which has O and asterisk 2 to the power of m space requirements. This allows the algorithm to efficiently store and reuse results for previously computed states, which is essential for avoiding redundant calculations and improving runtime performance. Comparing this optimized approach to a brute force solution highlights its advantages. A naive brute force approach would involve generating all possible assignments of workers to bikes, which can be represented as permutations of m bikes chosen for n workers. This would result in m factorial divided by m minus n factorial combinations in the worst case. The time complexity of such an approach is O, m, which grows much faster than O, n times m times 2 to the power of m. By contrast, the optimized solution restricts the search space to n asterisk 2 to the power of m states using memoization, making it significantly more efficient for larger input sizes. This reduction in computational complexity is crucial for solving the problem within a practical timeframe. To analyze the algorithm under different scenarios, we consider the best, worst, and average cases. In the best case scenario, even if the number of workers is small compared to the number of bikes, the solution still needs to process all n asterisk 2 to the power of m states. Therefore, the time complexity remains O, n times m times 2 to the power of m. In the worst case, where both n and m are large, the exponential growth in the number of states makes the solution computationally intensive. On average, the performance is governed by the same exponential factor, but memoization greatly reduces the number of redundant computations. This ensures the algorithm performs as efficiently as possible within the constraints of the problem. The mathematical justification for the time complexity of O, n times m times 2 to the power of m, lies in the fact that the algorithm evaluates each subproblem for all n workers in 2 to the power of m possible bike assignments, performing O, m operations for each state. Similarly, the space complexity of O, n asterisk 2 to the power of m, is due to the storage requirements for the memoization table, which holds results for all unique states. By balancing time and space efficiency, this solution avoids the factorial growth of the brute force approach, making it significantly more practical for moderate input sizes. While still exponential, the use of memoization in structured DFS provides a manageable trade-off between complexity and performance. When solving this problem, there are several common mistakes to watch out for. First, not handling edge cases properly can lead to incorrect results. For example, some solutions incorrectly assume the number of workers is equal to the number of bikes, but you need to ensure your solution accounts for scenarios where there are more workers than bikes, or vice versa. Second, failing to optimize for larger inputs can be a major issue. If you rely on a brute force approach, the factorial complexity quickly becomes infeasible as the number of workers and bikes increases. For instance, with 10 workers and 10 bikes, the number of permutations is far too high for practical computation. Another frequent issue is incorrect distance calculations. The Manhattan distance formula, which is the sum of the absolute differences between the x and y coordinates, is simple but prone to subtle bugs if parentheses or absolute values are misapplied. Finally, using a greedy approach without proper justification can lead to suboptimal results. While assigning the nearest bike to each worker may seem intuitive, it doesn't always lead to the globally optimal solution. It's crucial to validate that your approach aligns with the problem's constraints before relying on such strategies. Now, another common mistake is overlooking the impact of sorting. For instance, if you sort based purely on distances but ignore tie-breaking rules, such as the order of worker or bike indices, your assignments may end up incorrect. Always adhere closely to the tie-breaking criteria outlined in the problem. From an interview perspective, understanding constraints is critical. Interviewers often present scenarios where the number of workers doesn't match the number of bikes, or where input sizes are dynamic. Make sure to clarify these details upfront. When it comes to optimization, it's helpful to start with a brute force method, explain its limitations, and then build towards more efficient solutions, such as using greedy methods, priority queues, or dynamic programming. Additionally, you should clearly communicate how you handle tie-breaking scenarios. For example, if two distances are equal, are you prioritizing based on worker index or bike index? Finally, be prepared to analyze the trade-offs between different approaches, such as comparing the time and space complexity of brute force versus an optimized solution. For example, a priority queue might improve runtime but requires more memory, so it's important to weigh these considerations carefully. This problem also shares similarities with a few other LeetCode challenges, which can help you build a deeper understanding of assignment and optimization problems. LeetCode 1057, Campus Bikes, is a direct application of assigning bikes to workers based on minimizing distances, much like this problem. LeetCode 1383, Maximum Performance of a Team, is another optimization problem that involves balancing constraints to achieve the best outcome. Similarly, LeetCode 857, Minimum Cost to Hire K Workers, focuses on resource allocation under cost constraints, which parallels the decision-making process in this problem. Finally, LeetCode 1135, Connecting Cities with Minimum Cost, introduces graph-based optimization, where minimizing distances or costs is a key factor. By exploring these related problems, you can strengthen your skills in tackling a variety of assignment and optimization challenges. There are also several alternative approaches you can consider for solving this problem, each with its own trade-offs. Using a priority queue, or heap, is one option. This method is efficient for sorting and retrieving the minimum distances, with a time complexity of n log n. However, it does require additional space to maintain the heap. Another approach is the Hungarian algorithm or bipartite matching, which is optimal for minimizing costs in assignment problems. While it guarantees the best solution, it has a higher implementation complexity and a time complexity of n cubed. Dynamic programming is another viable method, particularly for smaller input sizes. It allows you to explore all possible assignments, but both the time and space complexity can grow exponentially, making it less practical for larger inputs. Lastly, a greedy assignment approach is fast and easy to implement, but it doesn't always guarantee optimal results unless the problem constraints explicitly allow it. Each method has its strengths and weaknesses, so selecting the right approach depends on the specific requirements and constraints of the problem you're solving. That wraps up our walkthrough of the Campus Bikes 2 problem. We discussed the brute force approach and its implications for solving optimization problems. Remember, practicing these types of problems helps build strong problem-solving intuition. Thanks for watching, and don't forget to like, share, and stay tuned for more coding solutions. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!